B and C side is called alpha. The angle between C and B is called C and B is called alpha. And what about the beta? Beta is between what angles? Because look here, this one side is your A, this one side is your C, between A and C. And gamma is between, this one is A and this one is B, between A and B. So we look, simple cubic cell is all three sides are same, equal, and all three angles are 90 and equal. Similarly, if tetragonal shape, we have like a different thing. A is equal to B, but the third side is not equal. All three angles are 90 degree.
Yep. Yeah, he's only going to focus on this one here. He said that he's not going to test us on any of these.
And even on this one, even on this, the packing is of three types. I will explain this thing. Packing here. Look here in this case example. This packing is like, for example, there are many unit cells. If it is on the corner, it is shared by other cell also. And if it is in the center of the cube, then it is only shared by one cell. It belongs to only one cell. But if it is at the corner here, it is going to be shared by this one, other one, maybe like many of them, many atoms shared. So look here in this case. There are two ways. Okay, now I will show you this one. Where is the close packing here? No, this is not the boundary. It's close packing. Where is that one? Like this. Closest packing. Look here in this case. Clearly there is a more empty space in simple cubic. Now look here, this one from here, this one. These, how many are present at the corner of the simple cube? How many sphere?
We have 8.
8, and 8 are shared by 8 other cells. So if you divide, each of this one is shared by 8 of them. So actual overall, if you consider how many sphere completely belongs to one shell,
only one.
So only one, because 8 divided by 8, 1 over 8 is going to give you 1. In this case, these 8 are again 8 divided by 8, 1, you will get 1. And 1 is in the center, which only belongs to this one. So 1 plus 1 is how much?
2.
2. In this case, the situation is different. Look here, in the values are already given here in the closed packing.
4, right?
A face-centered cubic cell contains 4 complete spheres. So in the simple cubic, you have only 1 belongs to that one, if you take an average. In the body-centered, what happens? 2. And in the face-centered, 4. So now let's go to the question number 44. Can you read the question number 44?
Yeah, let me see. What is it? Number
12.44.
Okay, calculate the number of spheres in these unit cells. Simple cubic, body-centered cubic, and face-centered cubic.
Okay, so I already told you, in simple cubic, 8, but shared by 8 others. So 8 times 1 over 8, you will get what? 1. In face-centered, what happens?
There's
1 is in the center, which is only belong to that cell, and the 8 other are shared by 8 others. So 8 divided by 8 is 1, and plus 1, 2.
Yep.
And what about the last one?
There's the 1/8 in each corner, so all those together is 1, and then you have one
On the
half cube here on the opposite side is the other half, that makes 2, and then this here
yes.
is 1/2, there's the other half that makes 3, and then there's
Mm.
1/2, and then the opposite 1/2,
Yes. So
so that
you
makes
get like
4.
a 4.
Yep.
Okay. That's the thing is then. Okay.
Yeah, that's
The
about
next.
as far as he wanted me to or us to go with
Okay.
that. And
Okay.
the
Okay. Do you want to do this type of question like this one or not?
no, no,
No. So leave it this one.
yeah, 12.47 was pretty easy.
What is the 12.47? Read that
It's
one.
asking vanadium crystallizes in a body-centered cubic lattice. So,
Okay.
and it says how many V or vanadium atoms are in a unit cell. So
Mhm.
it doesn't. I guess in this case it didn't matter. What it was, vanadium
Because
or whatever.
vanadium is what saying body centered. Am I right?
Body-centered.
So body centered we already know
Mm-hmm.
how many because 1 in the center
Yep. Plus
and
plus
8
1.
but divided by 8 because 1 over 8. So it's going to 1 1. So 2. So
Yes,
there are
sir.
2 vanadium atoms going to be there.
Yep.
It's
2.
clear?
Yep. And that was it.
So it is just look the body centered and you will get the answer.
Mm-hmm.
Okay, and let's do some qualitative properties. Okay. Mm,
After the colligative
mm.
properties, would we be able to brush over some of the molecular
Yes,
orbital energy level diagrams with like the
molecular orbital. Okay, so let's first
like
do that one. Okay.
the anti-bonding and
Okay, okay, let's do some that one. Okay.
I was just
Let's
trying
take
to.
the example of N2 molecule, nitrogen molecule. N2 molecule, nitrogen molecule.
I,
And suppose you have to not only write the electronic configuration, molecular electronic configuration.
I wanted to ask you though before we go
Mhm.
into an example is this thing was from the book.
Yeah, that's the same thing.
I
Yes, you're right.
when you and I were doing it, we I just wanted to know if in this case it didn't really matter because when we were doing them, we did this.
Yeah, sigma 2px,
But
2px at the bottom.
yeah, we did like
Hmm.
it was kind of like this,
Yes, normally the things are there.
right?
What is the example of this one?
Say again.
Second, because normally when I was doing, I was putting this one at the bottom.
Right, right. I just wanted to make
Okay,
sure
this one
like
at the bottom.
that's still what this is, right? It's
Yeah,
just
these are the
alternate.
same, but the only difference coming here. Am I right?
Right.
Now read the figure. Okay, read this thing.
Yeah. General molecular orbital energy level diagram for second period homonuclear diatomic molecules.
Lithium, beryllium,
Yep.
boron, carbon, nitrogen. For there are sigma 1s, sigma 2s orbitals have been omitted. Okay, the sigma 2 apex orbital higher in energy than either the sigma 2 px orbital is higher energy than 2py or 2p orbital. This means that electrons in the 2px orbitals are less stable than those in 2py and 2p. For O2 and F2, the 2px orbital is lower energy than. So because in generally, this one is lower energy and this one is higher energy.
Yeah.
But for these things, like these examples are given here, it is reverse for this case. Of course, for bond order, it doesn't matter in nitrogen. But if you are studying more in detail, like because these are the experimental things from here, because they make a triple bond, double bond, like those things. So in these examples, this is become reverse. This will become like a more stable because the electrons in the lower energy orbitals are more stable than sigma than the higher energy orbitals. So generally we expect this one as a lower energy and this one as a higher energy. But this is exceptional case for these molecules. for lithium, beryllium, boron, carbon, and nitrogen. It's clear?
Okay. Okay.
So only for these. Otherwise, for oxygen, fluorine, hyd, and other things, normally we take this one as a lower energy. But for nitrogen, carbon, boron, you take like opposite, make opposite thing. But in order to find the bond order, even if I use the old math system, still I will get the same thing.
Okay.
Let me, we will put here and see. Nitrogen. How many electrons are in the nitrogen in the p orbitals? 3. Am I right?
3.
And the same thing here is 3. Here it is also 3.
For nitrogen?
Nitrogen. And if you write that configuration for each nitrogen atom, 1s2, 2s2, 2p3.
2p3. Okay.
7 electrons. So now look here in this case. First I am putting one electron, you always put one electron if they are equal energy according to Hund's rule, and then pair up according to Pauli exclusion principle. So far I have added 4 and this will go to 6. How you are going to calculate the bond order?
So we do 6 minus 0 over 2, and that makes 3.
So even if I reverse it and I write like this, and 2 here, still they are all in the bonding molecular orbital. And 6 minus 0, you will get the same bond order. For bond order purpose, it's not going to affect, but there's like a experimental evidence, like in case of these atoms, they reverse.
Okay. And Joffrey, I just want to make sure I understand this. Say if it was like we just used nitrogen, right? Say if it was I just want to use like if it's like boron. So that's 1s2, 2s2, 2p, well, I guess 2p1, but that would only be, so I guess I want to make sure the order of filling these, so it'd be like 1 electron, 2, 3, 4, 5, 6, is that right?
Yes.
Is that right? So like you have your 6 electrons, so you're going 1, 2, 3, 4, and then 5, 6?
6. But in case of oxygen, if it is oxygen, let's take the oxygen or maybe fluorine. You have 4 electron in the 2p4 for oxygen I am talking about. 1, 2, 3, 4. The same thing with other oxygen.
Okay.
1, 2, 3, 4. And now what happens? Now I am going to write the sigma 2px first at the bottom, putting 2 electron 1 and then again 1, and then I will get 2 orbitals with equal energies, and I am putting 4, 4, 8 electron. I have 1, 2, 3, 4, and this is pi 2py equal to pi 2pz. In case of this one, again you can make pi 2py equal to pi 2pz, but this time it is a star, anti-bonding. And the last one is going to be sigma star 2px. But remember, x, y, z we are just giving in the order. Otherwise, even if I write sigma 2py and put 2p, x and z is going to be not wrong. But normally we write x, y, z in the order like. Is clear?
Okay. So you went 1, 2, 3, 4, 5, 6.
And now we have 2 more. If I put this one, is going to be wrong. Why?
It has to go here?
Yes, it has to go here. And now this oxygen molecule has how many unpaired electron?
2 unpaired.
Unpaired electron 2. So it is paramagnetic. It is what?
Paramagnetic.
Paramagnetic means at least 1 unpaired electron. At least. Maybe more. What about the nitrogen molecule? It's a paramagnetic or diamagnetic?
Diamagnetic.
Yes, because I don't see any unpaired electron, single electron. And what is the bond order here in this case, oxygen?
We have 6 minus 2, which is 4, and then over 2, which is 2.
2. So there is a double bond between oxygen. It's clear? If you take a fluorine,
Yeah,
fluorine has
I was going to say fluorine. Let's do fluorine. So,
1, 2, 3, 4, 5, 5. We have 5 electrons.
yep.
Now here we also have 5. 1, 2, 3, 4, 5. 2p5, 2p5. Now I'm taking the same thing like sigma 2px. Sigma. And putting 2 electron. Now in the next one I'm going to put like making equal energy orbitals. This is equal pi 2py is equal to pi 2pz. 1, 1, 1, 1. So far how many I have used?
2, 4, 6.
6.
And we have 10 to use, right?
10.
Okay.
So now I'm going to make another one here. Equal energy. This is going to be pi 2py equal to pi 2pz, but star anti-bonding. And the last one I'm going to take here, like you are right, this one is going to be sigma 2px star. So where I will put the next electron?
Okay, so we have 10 to use, and we've only used 6. So I'm thinking 1,
7,
8,
8, 9, 10. First of all, I'm
right?
asking, is the fluorine molecule is paramagnetic or diamagnetic?
This looks like it's. It looks like it's diamagnetic.
You're right,
there's
because
no
I don't
unpaired.
see any single electron.
Right.
So it's a diamagnetic. So first of all, they can also ask this thing. And what is bond order in this case?
6 minus 4 is 2 over 2, 1. And it makes 1 bond.
And in fluorine, we have a single bond. It's clear?
Yep. So again,
Okay.
if I was filling up these 10, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. I just want to make sure I'm. And if we were going to like provide this, let's see.
And because we are doing like in the bonding, we have two theory: valence bond theory and molecular orbital theory. Valence, if I use the valence bond theory for oxygen, I can't prove, cannot show paramagnetic property here by using valence bond theory. Even oxygen molecules show paramagnetic property, but valence bond molecular orbital theory can prove that oxygen molecule why it is paramagnetic, because it has single electron. Is it clear? Hello?
That's. I'm sorry, it was cutting out. So the valence bond theory cannot show it, but the molecular orbital theory can.
Can.
Okay.
And the other thing is, in valence bond theory, you have a concept of bond order of 1, 2, 3, but not a 1.5, a 0.5, or 2.5. Molecular orbital theory also gives the concept of not only 1, 2, 3, but also 1.5, even 0.5, even 2.5, something like that. For example, if I take the example of H2 positive. What is the bond order of H2 positive? Can you tell me by using the valence molecular rule?
Oh, let's see. Yeah, I can. I'll make. So H2 it should be 1s2, right?
H2 is, no, first write separately 1s1, 1s1, because each hydrogen has one electron, but you have a plus charge here. Plus means one electron has lost, 0. You have only one electron there. Am I right?
Yeah, you're correct.
So normally we have 1s1, 1s1, but plus means we have to remove and 0 electron. There's, don't put electron here. It's empty. Okay. Now you are making the same thing. Like, yes, that's good. What will be the name of the last, the bottom one?
Sigma 1s.
Sigma 1s. And how many electrons you have to put here?
It would only be 1.
1. And how many electrons in the top one?
0.
0. What is the bond order?
1/2.
1/2, because bonding is 1 minus 0 over 2 is 1/2, 0.5. You don't get the concept of half bond, 0.5 bond in the valence bond theory, but you get here. Am I right?
You're right. You're right.
What about this one? Try this one. He positive. He2, sorry, He2 positive. He we have 2 and positive. What is the bond order?
Okay. All right, so I'm going to say 1s2
Hmm.
and 1s2. And this will be sigma.
Okay, but how many you already have removing one electron from any one of them? So
Oh, it should just be 1s then.
1s1. One of them is going to have one less electron. Okay. 1s1. Okay, now you have total how many electrons?
Total of 3,
3.
right?
So what is the name of the bottom one?
Sigma 1s.
1s. What is the name of the top one?
Sigma star 1s.
Star 1s. Now put the electrons. What is the bond order?
Zero.
No, not
Oh, wait.
0.
2 minus 1 is 1.
Yes, 1 over 2. Okay. Half. This. What about this? He2 positive is paramagnetic or diamagnetic?
Paramagnetic.
Paramagnetic. That's right. Now we already have shown like O2 molecule is paramagnetic. Now I want you to, and also look here. I'm asking which one is more stable. Which one is, you also have to calculate the bond order, more stable. And for stability, higher the bond order, more will be more stable is the molecule.
Mm-hmm.
So I'm asking O2, O2 negative, O2 positive. 3 of them. And also tell me which are paramagnetic, which are not paramagnetic. bond order and which is the most stable, which is the least stable.
Okay. All right, let's see. So O2 negative, so or O2 1s2, 2s2,
You don't have to write
2p4.
1s2, 2s2, they are going to balance each other. Just go to the 2p things.
All right.
Because F1s2, 2s2 bonding, anti-bonding cancel each other. You can also use the square boxes, it's no problem.
Okay. Okay. So in O2,
How many total electron you have?
yeah, 2p4, so 8.
8. So now put 8.
So I'm going to call this one sigma.
2px. Even I can give the 2py, doesn't matter, but just follow the general trend
Okay.
in order. Sigma 2px, sigma 2py. And also put equal here because they have equal energy. Yes. And now 6. And this one, what is the name of the top one? Wait a minute. What you are writing here? I don't understand. What is here? 2py, 2pz?
Uh, yeah.
But you are forgetting pi.
Oh, it's pi.
Yeah, because that's pi.
Okay. I put sigma. All right.
Pi 2py, pi 2pz. Okay, what is the bond order? Two. So the bond order for oxygen is 2.
Mm-hmm.
Now do the same thing with O2 negative. O2 negative means it has, you don't have to make again, you can check again. O2 negative means
I'll use
you have more
I'll use a different color. Cool.
okay,
I'll
put
try.
extra electron, different color.
Right. So it's got O2 negative would be an extra one. So if that were the case, it'd be 1,
Mhm.
2, 3, 4, but 5,
Mhm.
right?
Okay, one of them has 5, yes.
So okay, so only one of them would have 5. Is that
Hmm.
and the other one would have 4.
So yes, total we have 9.
Okay. Okay.
Don't erase it. Just put the
Mhm.
extra electron where the extra electron will go.
Oh, okay. It'd go right here. Yeah.
Okay, so is it paramagnetic? O2 was paramagnetic. We already checked that one.
This one would still be paramagnetic, right?
This is still going to be paramagnetic because still we have one unpaired electron.
Okay. Okay.
I'm just writing PAR, paramagnetic. So O2 negative is still paramagnetic. What is the bond order now?
6 minus 3
Hmm.
is 3 over 2.
Hmm.
3 over 2? Does
Yes,
that make
right?
sense? Yeah. So 2 and a
Yes,
half.
1.5. Am I right?
Oh, yeah, 1.5.
Or 3 over 2 is okay. What about the O2 positive?
Alright, so O2 positive. So instead of having
Extra electron, you
8,
have
it's
one
going to
less
have
electron.
7. Okay. So there would only be 1 over here, right?
Yes, and it's still going to be paramagnetic.
Yes. And bond order would be 6 minus 1 is 5 over 2.
Mm.
So that would be
6 minus 1, 5 over 2, which is 2.5.
2.5.
Which one is going to be more stable? Yes, this is going to be more stable, then comes 2, then comes 1.5. And it makes sense. Because why? Because you have one less electron, which makes the electron-electron repulsion. It will decrease the electron-electron repulsion, am I right?
You're right. You're right.
In this case, you have like extra electron. So more electron repulsion, making it less stable,
Oh, it's the least stable of them.
least stable. It's
Okay.
clear? Like
Yeah,
this.
yeah. I definitely. I think that out of all the areas, this was probably my weakest point.
And also
So
when you have to write the configuration, sometimes you can make a like this also. You can also write like this start because we are not showing the sigma 1s. So you can write sigma 1s, then comes sigma star 1s,
yeah.
then comes sigma 2x, which we are not showing here. Then comes sigma star 2s, and then it comes like sigma 2px. And also how many electron we are putting? 2, sorry, 2, 2, 2, 2, 2px, 2 electron. Then we have pi 2py. Some depending on the book, some they write in the like together, pi 2pz, and they write total, whatever the total we have 4 here. And then we have pi 2p y equal to pi 2pz star. And how many electrons? If it is 2, 1, 3,
4,
whatever
6,
it is,
8,
you can write
10.
here like this. So we also write like this. This is called electronic configuration of the molecule.
Yeah,
Is clear?
I think I'm gonna have to, because I saw this way in the homework.
Okay. Maybe sometimes they write without parentheses, so you can check how they are writing.
Can I?
Okay.
I want to try one. I want to try S2 minus. Can I do that and
Which
you
one?
can. I want to try S2 minus.
Us.
That's sulfide.
Oh, you want that one? Okay.
Like S2 minus. Like if I
Uh,
so I'll do
like like this one, S2 minus.
no. What?
Hmm.
Let me see. Does this exist? S2 minus.
Yeah, that's also. But this is.
Oh
But
no.
how you are going to write the molecular configuration? For molecule, you need at least two atoms.
Oh, okay. Okay. No, I didn't.
Okay, we
Yeah, I
can
didn't
write S2
realize.
negative. That's no problem. Configuration. For this, you have don't have to write the molecular orbital theory. It's just a simple theory, simple thing.
Okay.
Because for sulfur, I can write like 1s2, 2s2, 2p6, 3s2, 3p4, like this. Now for S2 negative, because I have two less electron,
Mm-hmm.
so I'm going to write all of them as it is, but instead of putting 3p4, I'm putting 3p, how
Two.
many?
Two.
No, sorry, minus, this is a minus charge. Sorry, I
Oh, 3p6.
6, 2 extra, so
Okay.
6.
Okay.
If it is positive, then you remove the electron.
Okay.
But this is
Okay.
not a molecular orbital theory. This is a single atom,
Oh,
one
okay.
atom.
Okay.
For molecule or molecular thing, you need at least two atoms.
Thank you for for pointing that out to me.
Okay?
Okay. Okay. Yeah. What if
Mm.
yeah, maybe like could we is sulfate something that would be too much?
Let's try NO. The
No.
sulfate they are not going to
Okay.
give you. They will give you only
Okay.
diatomic molecule. Let's take NO. Even they are not going to give you different atom, but let's take similar type of things.
Okay.
So let's nitrogen has what configuration?
1s2, 2s2,
1s2, 2s2, 2p,
2p3, 3,
3, right?
3. Yep.
1, 2, 3, 1, 1, 1. And what about oxygen?
It's got
1s2,
yep.
2s2,
2p4.
2p4. 1, 2, 3, 4. Now I want you to write the molecular diagram and configuration for NO. So you can skip these two. Okay, they are going to balance each other. So I'm just going to 2p3 and 2p4. 2p3 is for nitrogen. 1, 2, 3. 2p4 I am writing for because I don't exactly like which one is higher energy, lower energy, so I'm just keeping equal.
Oh wow, so this is
Otherwise,
how we would
sometimes,
do it, one on each side?
yeah,
Okay.
sometimes they put, because they know the experimental values, the books one, so they put a little bit lower or higher. That's because we don't know the experimental values. I'm just putting equal. So this is 4. Now, if you make this one
Mm-hmm.
again, what you will go do?
Okay. So I'll label these first.
Hmm. And then again from here,
Okay, I have 7 to work with.
the one you are missing when you have, yes, because the number of molecular orbitals are going to be same as the number of atomic orbitals. You have three orbitals, three orbitals, atomic orbitals. These are the atomic orbitals. These
The
are what?
oh,
Atomic
okay.
orbitals.
Oh, so these okay.
And these are the molecular orbitals. So number are going to be equal. Yes, like this. Clear? And
Hmm.
is the molecule is going to be paramagnetic or diamagnetic?
Paramagnetic.
Paramagnetic.
Wow.
It's clear?
Yep. Thank you. That's
So
good. No,
what next?
that's good. I'll be able to. I'm gonna do some more self practice tonight
You can
and
try
tomorrow.
by yourself. After that, CO.
Yeah.
Of course, they are going to give you, I think, similar thing,
Yeah.
not the different thing, but you can try the similar thing, like like a heteromolecule with different two atom, but similar type things.
Okay. All right.
Okay.
I'm gonna try this one. All right.
Okay. Hmm.
Okay. Carbon. I got 1s2, 2s2, 2p2,
Two.
2p2. Okay.
Hmm.
And then we got up to 2p4.
Hmm.
Okay. So that means 1, 2, and then
Hmm.
1, 2, 3, and we'll do 4 right here. Okay. So I have 4, 5, 6 to work with. 1, 2, 3, 4, 5, 6. This looks diamagnetic.
Hmm.
It's gonna be
You're right. So it's clear.
yep. So
And
these
if you have to write the configuration in that way, like sigma 1s, something like that, how you're going to write?
yeah, I want to see if I get this right. All right, so I would have to account for everything here, right?
Hmm.
So it'd
Yes.
be um it'd be sigma 1s2
Hmm. Hmm.
uh sigma star
Hmm.
1s2
Hmm.
yeah, sigma whoops. Sigma 2p. Hold on. Sigma 2p 2. Yeah?
But it is XYZ, you have to mention 2p.
Yeah, so since this is the 2px and y
Hmm.
and z, what is it? Sigma 2px. Do I put 2?
Yes. Okay, which one? Sigma 2px2. Yes, you're right.
Yeah, okay. And then
And for the other one, depending on your book, you can write because they are equal, so you can write pi 2py equal to pi 2pz. And you can write separately or you can write total 4 here. Maybe like this. Or you can write 2, 2 on both of them. Look the pattern your book is using.
oh, okay. I think actually I recall seeing that. Yeah, I'm gonna load it up there in just a second. Right there.
You can put 2, 2 also, 2py2 and 2 star 2pz. Oh, it's here. Okay, they are showing. Okay, no problem.
Did it load
Yeah,
up?
yeah, that's load up. Okay,
I don't.
that's right. That's right.
Oh, right here.
They are writing. They are not putting the parentheses. Okay, they are putting at least like a equal. Okay, can you see this thing?
Yeah. Sigma
So
1s.
yeah, so you can write like this. For example, you're writing 2 here. You don't need to put less than they had given you the thing, but you don't need this one. You can put comma if you're writing that because that is
Yeah,
to
yeah.
showing which one is of less energy.
Right,
The
right.
less than we don't need. Okay,
Yep.
so you can write the same thing like this one, sigma 1s, then sigma 1s 2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma sorry pi 2py equal to pi 2p. You can put either 2py 2pz together like this 2 2, or you can put in the parenthesis 2py equal to pi 2pz and put total like 4 also.
Okay.
Is better you can put in parenthesis and then all like this. It's okay. It's clear?
Yep. Yeah.
Any question?
No, that's good. This is I just have to brush over this stuff here, and oh, okay, 4 there. Yep. And the
Ask
4.
your teacher before doing. There is some exceptional cases.
Yeah.
Like this one is less energy in nitrogen, but not in the oxygen. In oxygen, this one, sorry, no, sorry. In generally, it is 2px is less energy, and these are higher energy. But even from your book, it is saying like in nitrogen, it is reverse this order. So ask this thing before your exam, okay? Do I have to follow the when you are writing the nitrogen configuration? Either you will follow the regular routine or reverse it, bringing it here and this one there, okay?
Okay.
For nitrogen. Because normally we follow this thing, even for nitrogen. Because nobody knows experimental thing and we generally follow the general thing.
Okay.
But in case if he wants to, you can tell him, ask him before.
Will do. Will do. Yeah, I'm definitely gonna review all of it, all this stuff here.
So any question about this?
No. I'm gonna review it on my own, and I'll let you know if I have any questions arise and difficulties. I'm gonna do some.
Okay.
I'm gonna try
And
to
you
do
can
some more
stop whenever
practice.
you want.
Okay.
I put like 100 minutes, but if you want to stop, you can
Yeah.
just let me know. It's no problem.
Okay. Yeah. Do you have any? You know how you gave me that practice worksheet? Do you have any worksheets that kind of test knowledge on what we were doing there, the bonding and the anti-bonding? Do Do you have any worksheets
Okay,
that
I
deal with
don't
that
think, but
one? No.
I'm going to make it. No problem.
No, it's okay. You don't have to do it. I'm gonna search my book and see if I can find some more
I will
problems that.
also try to find somewhere, and
Okay.
I will, if I will get it, I will give it to you. Okay.
Okay. Yeah, that's out of like all these last three sections,
Mm-hmm.
that one area with those diagrams was just the one that I wasn't too confident on, but now uh, I think I'm definitely more confident in it now, and
Mm-hmm.
I'll be able to increase it. And once Thursday comes, you know, I
Okay.
think I'll be good. I'm hoping
Mm-hmm.
he if you know I'm sure that I'll see that on the exam, but I'm hoping that he sticks with the type of examples that were on the homework, like lithium, Li2, Li2 plus, Li2 minus, things like that.
Mm-hmm. Okay.
So I'm hoping he just sticks with those kind of like smaller elements. But
No, no, no. For molecular order, they are not going to give you too complicated. They will give you like maybe He, H positive, H2, maybe oxygen, those things.
okay,
For nitrogen, ask the question. Ask him. Do you have to
will
follow
do.
the regular thing or just reverse it the sigma 2px and pi 2py pi 2pz?
Will do. Also,
Okay.
I asked him about the if he was gonna give us the KF value and like the
Yes,
freezing
Kf
point.
value and Kb values they are going to give you, but
Yeah.
I still recommend to memorize the water thing.
Yeah.
For
1.8.
Kb, I think it is 0.52 Celsius per molar, and for Kf for water it is how much? 1.886. I think double check this
1.86.
thing. It is for water. And also you have to keep in memory what is the freezing point of water in
Is that
Celsius, 0 degrees Celsius.
0? Okay.
What is the boiling point of water?
Yep.
100 degrees Celsius.
100.
Why? Because if they give you the boiling point of solution is 102 degree, boiling point of aqueous solution,
Oh, okay.
aqueous solution. So you don't need, you need that delta TF. How you are going to know the delta TF? Because you know that the boiling point of water is 100. So it's going to be 102 minus 100 is going to be 2. Am I right?
Yeah, yeah. So it's basically like saying, okay, aqueous solution. We imply water. We can
Water.
imply
So
water is the solvent.
yes.
Okay. Okay. I
So
got you.
for water, I recommend to at least know the
Know
boiling
that.
and
Yep.
freezing point and these things. Others they are
Got
going to
it.
give you.
Yep. This was right. Yep. All right. Yeah, I'm
Okay.
going. This what is this worksheet here? This is
This is colligative properties.
okay.
Okay, let me I will ask one question.
Okay.
You can, if we can stop here, it's not big deal.
Yeah, if you
And
wanna
let me I will ask.
you
I'm
can
going to ask one question just
yep.
from the colligative properties. I have suppose you have 0.1 molar NaCl solution, aqueous solution. All of solution are aqueous, all of them. 0.1 molar MgCl2 solution, aqueous solution, and 0.1 molar glucose solution.
Oh, this.
I am asking whose which one has the highest boiling point? Concentration I gave you same, all of them.
Is it this one?
That's correct. Why? Because it's one half factor. I is going to be 3, not 0.3. Yes, effective molality is going to be 3. Effective. Because 0.1 times 3 is going to be zero point 0.3. That's right. What will be next? That's correct. And which one is going to be the last, lowest boiling point? This one. What about the freezing point? Which one is going to be the highest freezing point? Let's take which
So
one is the
does that mean
lowest
like
freezing point.
lowest freezing point? Okay. So would that be like magnesium chloride too? Like it would
Yes,
magnesium
yes,
chloride would need it to be the coldest to
yes.
for it
So
to
it's going to
freeze.
be like a least freezing point because there's a more depression in freezing point here.
Okay.
Okay,
More depression.
like
Okay.
this.
Yep.
Now, which one has the highest, lowest vapor pressure in this case? Lowest vapor pressure.
Would it be glucose?
No, again, the
No.
lowest is this one.
The lowest vapor
Because when
pressure.
you make the solution, the effective molality is 0.3 here. So it's going to be more decrease in vapor pressure, lowering in vapor pressure.
So the difference would be the greatest.
Yes,
Okay, I was thinking the which had
because
the
vapor
lowest
pressure go
difference.
down, freezing
Okay.
point go down, only the elevation point, boiling point goes up. And also the osmotic pressure. I don't know whether you did osmotic pressure or not, the last colligative property.
Yeah,
Osmotic
he
pressure
mentioned it in
is
the
also
lecture, but he didn't give us any homework problems on it. So that means that
osmotic
it's.
pressure is also colligative property.
Mhm.
And the same thing, because this MgCl2 has effective molality higher, we go 0.1 times 3, it has higher osmotic pressure. It has higher osmotic pressure. So in this case, I am summarizing this thing here
Mhm.
for this situation. 0.1 molar out of these three, whatever I gave you. Highest osmotic pressure, lowest vapor pressure, lowest freezing point, highest boiling point. It is summarizing everything here out of these three.
Got it.
It's clear? Okay, let's stop here. Okay.
Yep.
Any question if you want to ask?
Yeah, this this definitely covered the area that I needed to go over at this point.
Yeah, maybe next time we are also going to do some. It's not difficult. It's very easy.
Okay.
You already have done the gases law, am I right?
The gas law. Yep.
And the same rule and same general gas law apply here also. So it's not a big deal. Okay. So in the next session, I'm going to explain this some problem from here also.
Okay. I think unless I come up with any questions between today and tomorrow, would you be willing to meet with me for a
Yeah,
little,
you can
a
just
little
let me know
review?
what time is good
Like-
for you, and I'm
like-
going to meet with you.
Like
okay?
Wednesday, are you available at all Wednesday? That's,
Yes,
that's the day
Wednesday,
before my
Wednesday
final.
I'm going to available. Yes.
Okay. Yeah, tomorrow I'm going in. I gotta go into class for a review session that he's having for the class, so I'm gonna go and see what he's gonna say for that.
Yeah,
And,
whatever he is doing the review problems,
Mhm.
things, note those things because that will give you big help because it will tells you like what type of problems you want to do.
Yeah, I'm gonna ask him about the osmotic pressure. I'm gonna ask him about the nitrogen. I'll be able to ask him about all those things.
Yeah,
tomorrow.
ask about the nitrogen.
Okay.
Write both configuration. In one case, write the sigma 2px first and pi 2py, pi 2pz after that. And write another one which is pi 2py, 2p, pi 2pz. Say which one I have to follow for and show the picture from the book. Okay.
Okay. Okay. Yeah, that picture that I sent to you. Okay.
Yeah.
Okay, for sure. I'm gonna definitely do that. Okay. All right, Joffrey, that definitely helps big time. Thanks for clearing that up and helping me out. How was the that worksheet that I did? Did I do?
Actually, I checked a few of them, not completely, but it looks good, very good.
Looks good. Okay.
That's why I told you because if you keep in mind like A, B, and there is 0, but if they are not saying 0, then how I know that it's 0 lone pair?
No, you're right.
Okay.
Thank you for.
And I also ask that question from your teacher. Like say
Okay.
if it is AB 2,
Yep.
do you have to assume it is 0, or do you have to assume like 0 lone pair, 1 lone pair, 2 lone pair, like that?
Okay. Will do.
Okay.
Hey,
So
thanks.
before the exam, you can ask those things.
I will. I
Make
just
it
wrote that down. I wanted to say thank you also for you know, training me to think about like like on the worksheet that you gave me. It was like questions for a lot of
Mm,
them. It was like maybe for question 4. It was like molecular geometry for CS2. So it's like
mm.
you taught me to think about same as something I know CO2, and then for like number 5,
Actually, I love problems. So
you
I
know.
want like to you. You also to work very good, and you are very good in the problems. It's no problem.
Thank you. Yeah, like
Mm.
like number 5 was it was like SiH2Cl2, and I was like, it's just like CH2Cl2, AB4,
Mm.
and then PHCl2 is just like NH3, and
Yes.
CH CHCl3 is just like CH4,
Yes,
and
four.
then
Yes.
SF2 was just like
Yeah. So you can
H2O,
correlate and you
you
can
know.
easily get things.
Yep, PF4 plus was just like NH4 plus. So, those that doing it like that, like yeah, it was definitely it
No problem.
definitely
You are
helped
doing
help
very.
me do them faster. You know what I'm saying?
Mhm.
So,
Yes.
all right, I appreciate it. I'm gonna get to work, and yeah, I'll let you know if I have any more questions, and I'll definitely talk to you either today or I'm sorry, either tomorrow or
Okay.
Wednesday. Okay, I'll give you a
Okay.
call.
Okay. Okay.
All
No
right.
problem.
Thank you so much, Joffrey.
Goodbye.
All
Take
right. Have
care.
a
Good
good night.
night.
Good night.